So today we will be continuing with those aromatic electrophilic substitution reaction for the aromatic compounds. Yesterday we have discussed about the bromination reaction in presence of the Lewis acids. Normally, it's not happening. It's not normal for the aromatic compounds to react with bromine, because you know that bromines have the reactions with they can easily react with the alkenes. They undergo the addition reaction that is very fast. But in case of the aromatic compounds, it's not the addition reaction, it is actually the electrophilic substitution reactions. And we certainly need certain uh, Lewis acids, because normally this halogen bond, that is the halide-halide bond, bond between two of the halogen atoms, this is not very polar. So we need to create polarity in this bond, because two similar atoms are joined together. This is a non-polar bond, covalent bond, but we need to induce polarity in this bond, and that can only be done by using the Lewis acids. Lewis acids pulls some of the electron from one of the atom of, and then the other, there is a partial bond formation between the Lewis acids and the one of the halogen atom, and then initially, and then later on what happens, that partial bonding, which is has been shown in the transition state, that turning out into the true bonding. So we are left with only one halogen atom with positive charge, which is of course can be called as the electrophile. So once this electrophile is being generated, then it will be easier for the benzene ring, which is a nucleophilic center, to attack on this nucleophile and to result into the electrophilic substitution, substituted product. Slide number 27, you can see that just like the bromination reaction that we have discussed yesterday, the chlorination reaction of the aromatic compounds is also possible. So the chlorine molecule, the benzene ring undergo the electrophilic substitution reaction for the chlorine molecule also, uh, just like the bromine, but here we are using the ferric chloride, FeCl3, and the same mechanism can be followed for this also. There will be an initial formation of the carbocation, and then aromaticity will be lost, carbocation generation, and then what happens that FeCl4 negative will abstract one of the you know proton, and then what happens, it will be the aromaticity will be regenerated, and then one of the chlorine will be substituted with the hydrogen, and so we will get this. So whether that is bromine or that is chlorine, the reactions are very feasible. Reactions are possible. Iodine can also undergo the same reaction, but here you need to have one of the strongest oxidizing agent in order to create the electrophile, a good powerful electrophile, that is the I plus. You can see that on the slide number 28 that I have provided to you in the PowerPoint. So on that slide number 28, you can see that first of all, one of the oxidizing agent is used. For instance, you can use the copper +2 as an oxidizing agent, or you can try any other oxidizing agent like the peroxide, which resulting into the I plus formation. Once this I plus is produced as a powerful electrophile, then the rest of the mechanism is same. Benzene has to react on the I plus. There is the loss of the aromaticity and formation of the carbocation, and then base has to abstract that proton, and then there is a regeneration of the regain of the aromaticity by the compound, and resulting into that iodobenzene. The overall product, 65% of the product resulting. So there's also possibility of the other whether that is bromine, whether that is chlorine or the iodine, the reactions are possible in all these. But what about the fluorine? Fluorine is a small molecule, and this FF bond, this is very much polar bond, and this intermolecular distance interatomic distance very small, and it will be very difficult for the for anything to polarize this bond. That's why this reaction is usually not happening, because this bond is highly uh, strong, a non-polar bond. It cannot be polarized by using any kind of the oxidizing agent or any kind of the Lewis acids. And that's why this reaction is not very common. Halogenation reaction, electrophilic substitution reactions of the halogen. For all these group of halogens, there's a separate methods for the polarization of this bond, but ultimately all the bromine, chlorine, and iodine, they are undergoing the electrophilic substitution reaction with benzene, but very difficult for the reaction of benzene. These are the kind of the reactions that you are very much familiar with. You have studied these reactions in detail in your FSC level, but here we are discussing some new things related to these reactions. What happens, benzene reacts slowly with the hot concentrated nitric acid to produce the nitrobenzene. But the reaction will be much faster if it is carried out by heating benzene with a mixture of concentrated nitric acid and concentrated sulfuric acid. So if there's a direct reaction of the nitric acid with benzene, there will be no reactions, or very limited reaction. But if you are using the high temperature as well as the mixture of the nitric acid with the sulfuric acid, then the rate of the reactions will be very much high, and then because there will be a high degree formation of the nitronium ion, which is of course the single electrophile producing this reaction. So whether that is the nitration reaction, or whether that is the halogenation reactions, or any other type of the electrophilic reaction, the first step that we are doing is to produce the electrophile. In case of halogen, you saw that we were producing that halogen plus, and here we are producing the NO2 plus. So this NO2 plus is the electrophile. This is electron deficient center, electron deficiency with the nitrogen, and then what happens, benzene is going to react on this electron deficient center to produce the respective nitrobenzene. And how to do all this, we will be discussing in a stepwise. Is that the nitric acid, as you know, is that the nitric acid is used in combination with the sulfuric acid. The first step is that the nitric acid, the oxygen of the nitric acid, abstract a proton from the acid, from the sulfuric acid, and then there is a formation of the oxonium ion, O plus ion, and then the electron, the bond between the oxygen and nitrogen is shifted towards oxygen, and this oxonium ion, this water molecule is removed. So the very first step in the nitration reaction is the abstraction of the proton by the nitric group, NO3 group, from the sulfuric acid. The second step is the removal of the water from this intermediate, and then there is the formation of the remember nitronium that each step of this reaction is reversible. I mean, abstractions of the proton by the nitronium to produce the intermediate, and then intermediate that is losing the water molecule. All these steps, they are reversible. What you all need to do is to remove the extra sulfuric acid to avoid the uh, uh, I mean, to remove the water to avoid the back. Once you are getting this nitronium ion, now it's very easy for you, following the same mechanism where the benzene, the double bond of the benzene is attacking the nitrogen, producing that O negative, and then producing the carbocation. There will be a positive charge formation on the benzene ring, and then what happened, the neighboring carbon to this carbocation will lose its proton, and that proton will be abstracted by water to produce the nitrobenzene molecule. So this is the overall mechanism for this nitration. So you can see that detailed mechanism on slide number 32. I have shown the detailed mechanism of this reaction on slide number 32. I don't think that I need to show you the energy profile that I have shown you yesterday about the for the halogenation reaction, electrophilic halogenation reaction of, because that same kind of the energy profile diagram can be drawn for this as well. You have to show that initial, intermediate formation, transition state, intermediate formation, and then that intermediate is going towards the final product, and then showing each and everything on that energy profile. Since we did this, I don't think that we need to repeat that again. So you can draw, but there is only change of the intermediate. For instance, we have the reactant which are benzene and the nitric acid and the sulfuric acid. We have the intermediate of the carbocation formation, and we have that as well as the nitro NO2 positive, and then we have that final product, nitrobenzene. So you can draw that on the energy profile diagram, and showing that what are the transition state, what is the intermediate. You can show each and everything on that. Today I have this is not assignment, but a small homework, piece of the homework you can search out. And the task is that how we can reduce this nitrobenzene to aniline. I am also going to show you that which reagent will be used for this reaction. They are the tin chloride, H3O positive, following by the reaction of base. So using these reagents, how the nitrobenzene is going towards aniline. Can you draw the mechanism for this? I'll be happy to see that how many of you responding. In fact, you all need to do practice on this, that how the nitrobenzene is, what is the mechanism for this reaction. So if you share that, that will be good for you, for the information of all you. Next is the aromatic sulfonation reaction. As is, it's evident from the name, sulfonation means the addition of the sulfonic group. Substitution, this process of substitution of hydrogen of the benzene ring by SO3 group How this happens, and then what will be the mechanism for this, we will be discussing about this. But this reaction again is happening with the mixture of the sulfuric acid and SO3, that is called the oleum. We usually use the oleum for the reaction of the sulfonation reaction of benzene. Oleum, which is the mixture of sulfuric acid and SO3. What are the reactive species? Is sulfur trioxide or its conjugate. So as I am saying you that there's an initial formation of the electrophile. We need to have an electrophile first, and then benzene ring is going to attack on that electrophile. Here the electrophile is the SO3 plus, so SO3. Now question is that how SO3H plus. So how to create this? Remember this reactions occur at 25 degrees centigrade using the concentrated sulfuric acid. The product we already know that this is the benzene sulfonic acid. But I am asking about the mechanism. What is the mechanism for this reaction? Two molecules of the sulfuric acid react together. They produce the SO3, and they also produce the H3O positive as well as the HSO4 negative. So these are the things which are in equilibrium. After this formation of this SO3, now this SO3 has to react with the benzene ring. Because this SO3 positive, as you see, this is electron deficient center, and the electron rich center, which is the benzene ring, push its electron pair towards this SO3 towards the sulfur, and then we have the O negative formation, and we have this intermediate, the resonance intermediate, and then what happens, this HSO4 negative abstract a neighboring proton, and then there is the formation of the, there is the regain of the aromaticity, and we have that product where SO3 is added to the benzene ring with the still carrying O negative. A negative charge on oxygen is still there, but since we have this mixture, since we have the acid in the form of H3O, and that O negative is abstracting proton from the H3O, and then finally we have the benzene sulfonic acid. So this is altogether a four-step reaction. First step is the formation of SO3. Second step is the reaction of benzene with the SO3, formation of the resonance intermediate. Third step is the regain of the aromaticity, and the fourth step, of course, is the abstraction of proton by this O negative. So altogether these are four steps. You can see this mechanism on the slide number 36, and of course you can draw the energy profile diagram for this by using the same way that we did for the halogenation or for the nitration. You can show the benzene and the sulfur and the sulfuric acid as the reactant. The intermediate could be the carbocation, and then finally we have the benzene sulfonic acid as the final product. You can show that on the product position, and you can show the energy profile diagram. We have some practical application of this sulfonation reactions, where you have seen that this reaction has been used in the antibiotic formation. For example, the sulfanilamide is a compound where this reaction has been used to produce the sulfanilamide antibiotic. Similarly, these reactions can also be used for the synthesis of the cresol, which is the hydroxytoluene or phenol. You can say that it's the paramethyl phenol, which is also called the cresol. So this is the this is the end of this lecture, and I expect that you will be sending that small homework to me, and you will be sharing. And if you have any question at this stage, you are most welcome. And thanks a lot. Have a good day.